In this module, we're going to start expanding a little bit more on this expression of Kc, this equilibrium expression or equilibrium constant expression. You need to be able to write these expressions. And we've talked about how to write them. We're going to get a lot more practice throughout this chapter and for chapters to come on writing them. Hopefully this will become second nature very quickly. You also need to be able to calculate the value of Kc from a knowledge of the equilibrium concentrations or pressures of reactants or products, or if you're given initial concentrations and the equilibrium concentration of at least one substance, you should be able to calculate Kc as well, the value of Kc. You can also use that equilibrium constant or Kc value to calculate equilibrium concentrations. You should be able to use the equilibrium constant to qualitatively predict the extent of the reaction. What do I mean by qualitative? Remember qualitative and quantitative. Quantitative is a value, an actual measurable number. Qualitative is more about perspective. It's like how I say a solution is concentrated or dilute, that's compared to another piece. So qualitative is giving us an idea of where the system's lying, but not giving us actual values. You should be able to tell me, is the reaction product favored, reactant favored, or truly forming equilibrium? And be able to calculate your reaction quotient Q. Q and K are calculated the same way, but they mean different things. And so you need to be comfortable with what Q is, comfortable with what K is, understand their differences, and understand how to compare them. Q and K stay with us through most of the rest of the chapters throughout this course. Determine whether a reaction is at equilibrium, and if it's not in equilibrium, predict in which direction it will shift to be able to reach that equilibrium. So first, let's discuss this magnitude of KEQ. If Kc is very large, meaning greater than 1,000, it's mostly products at equilibrium. If Kc is very small, meaning 10 to the negative third or smaller, it's mostly reactants at equilibrium. In between there, it's forming equilibrium. Now, truthfully, anything above 1 is considered to be reactant, or anything above 1 is considered to be product favored, and below 1 is considered to be reactant. But if we have large Kc values, it's mostly products. You have very little reactant present. And if it's a very small Kc value, then mostly reactants are present. We have very little product. So what Kc is telling us is the extent of the reaction. It's telling us, how much do I have? What is the extent of this reaction? Appreciable, meaning a measurable or observable amount, has the reaction produced an appreciable amount of product? Or is there an appreciable amount of reactant still present? So let's try to do this ourselves. Let's predict, is K large or small? If I look at this first reaction here, N2 gas plus O2 gas give me 2 moles of NO. I see that the little blue circles are N2, the little red circles are O2, and then the little blue-red diatomic is the compound NO. Let's count them up. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4. And 1 and 2. What do you think? Do I have more product present or more reactant present? I've definitely got more reactant present, right? So I expect this to be reactant favored. What if I wrote out the Kc expression for this? Here's my Kc expression. Let's plug in the numbers we have. Let's pretend these are the concentrations we have. I've got 6, 4, and 2. Is this value going to be big or small? It's going to be pretty small, right? It's small. It's reactant favored. I have more reactant present than I have product present, which makes my denominator larger, which makes my ratio smaller. What about the second system here? H2 gas plus Br2 gas giving me 2 moles of HBr gas. H2 gas is this little white dot. I've got one of them. Br2 gas is this light brown diatomic. Got one of them. And 2 HBr. 1, 2, 3, 4, 5, 6, 7, 8, and 9. It's definitely product favored. What's my Kc expression? I've got HBr squared, because remember that coefficient out front becomes your exponent, times the concentration of H2 times the concentration of Br2. Let's pretend that those molecules are actually a molarity instead of just number of molecules. That would be 9 squared divided by 1 times 1. Overall, the value would be 81. That is Kc value that's larger. It's product favored. So what is a reaction quotient then? Well, reaction quotient is actually calculated the exact same way as Kc. The difference is that Kc is your equilibrium expression. It's the quotient of your reaction at equilibrium specifically. The reaction quotient, or QC, is your reaction quotient at any point in the reaction. So what if the reaction is not at equilibrium? Then we use the reaction quotient QC instead. Again, it's calculated the exact same way, that products over reactants. We see we've got C raised to the power of C times D raised to the power of D divided by A raised to the power of A times B raised to the power of B. So calculated the exact same way. The only difference is Kc is your equilibrium expression. It is the reaction quotient at equilibrium specifically, whereas QC is your reaction quotient at any point in the reaction. If QC is less than Kc, the reaction will proceed in the forward direction, meaning forming more product. If QC is greater than Kc, the reaction will proceed in the reverse direction, meaning forming more reactant. Reactant in the sense of the way the reaction is written. If QC equals Kc, the system's at equilibrium. The way I think about this is I think about a number line. I put Kc in my middle, and then I compare where QC is to that. If QC is smaller, it wants to chomp its way forward. To do that, it needs to make more products to be able to reach Kc. If QC is bigger, it's going to chomp its way backwards. It's going to react some of those products to make more reactant. Based on the way the reaction is written, it's going to form more reactant so it can reach Kc. The goal is to reach equilibrium. The system is at its most stable state when it's reached equilibrium. Remember, chemistry is basically minimize your energy, create disorder. The way to minimize this energy is to reach an equilibrium. So QC is going to tell me which way the reaction is going to go to minimize that energy. Let's work a few examples. Let's say I have a 1 mole sample of SO2-Cl2 gas, and it's allowed to come to an equilibrium with SO2 and Cl2 in a 2-liter flask at 30 degrees C. At equilibrium, the concentration of SO2 gas was found to be 0.0239 moles per liter. And then it gives me the reaction, SO2-Cl2 in equilibrium, remember these are equilibrium arrows, forming SO2 gas and Cl2 gas. And it's 1 mole, 1 mole, 1 mole across the board. So first, find the equilibrium concentration of each gas in the flask. Well, let's see. It tells me that I have a 1 mole sample of SO2-Cl2. It comes to equilibrium with SO2 and Cl2, and it's in a 2-liter flask at 30 degrees C. At equilibrium, the concentration of SO2 is found to be 0.0239. What I'm going to do to solve this, first, I need concentration. And then we're going to talk about ice or rice tables. You can call them ice tables or rice tables. I don't care which one you call them. But first, let's find the concentration. The starting concentration of SO2-Cl2, I'm going to put a little I for initial. I've got 1 mole, and I've got a 2-liter flask. Because it's a gas, it's going to expand to take up that whole entire area, so I know the volume of my gas is going to be 2 liters, and I find the concentration to be 0.500 molar. Now we're going to set up an ice table, or a rice table. Again, you can call it whichever you would like. I learned them as ice tables, other people learn them as rice tables, and I'll explain what those words come from in just a sec. First thing you do is write down your reaction. Then, and if you want the R in there, that's fine, you're going to write down the initial concentrations of each species, the change in the concentration of each species as the reaction proceeds, and the equilibrium concentration of each species. So write down what we know. We know that we're starting with 0.500 molar SO2-Cl2. We also know that to start, we don't have any SO2 or Cl2 present. How do I know that? Because I'm told that a 1 mole sample of SO2-Cl2 was allowed to reach an equilibrium. It didn't tell me it put any SO2 or Cl2 in to start, so that means that we only have SO2-Cl2 at the very start of the reaction, and we don't have any of our product at the very beginning. We know this is reacting in a 1-to-1 mole ratio. 1 mole of SO2-Cl2 will decompose to form 1 mole of SO2 and 1 mole of Cl2. But we don't know exactly how much is going to react. So we're going to use a placeholder, X. We're going to say minus X. X is representing that number of moles that's going to react. Specifically in molarity though, because rice tables or ice tables are set for molarity. We know we will produce X SO2 and X Cl2. Why X? Because again, it's a 1-to-1 relationship. If there was a 2 out here, we would put a 2 here. And then at equilibrium, we have what's left over. We know we have 0.500 minus X, X, and X. Now, the rice or ice, R stands for reaction. I stands for initial, and that's initial concentration. C stands for change in concentration. And E stands for equilibrium concentration. So I call them ice tables, initial change equilibrium. A lot of students call them rice tables because they have to write the reaction first. Again, I don't care which way you call it. You need to be able to recognize it when I say it either way. How am I going to solve this though? Well, here's the thing. It tells me that equilibrium, the concentration of SO2 is found to be 0.0239 molar. So I actually know what that value of X is. This equals X, which means at equilibrium, this also equals 0.0239 molar. And it means that equilibrium SO2-Cl2 is 0.500 minus 0.0239, which gives me 0.476 molar. So, find the equilibrium concentration of each gas in the flask. Pause if you need to write any of this down because I need to erase to write all this out. The concentration of SO2-Cl2 at equilibrium is 0.476, and that is molar. Concentration of SO2 at equilibrium, 0.0239. Molar, and the concentration of Cl2 is also 0.0239 molar. So I've answered the first part of the question. Now, find Kc. That doesn't just mean the Kc expression. If I just wanted the Kc expression, I would say just expression. Find Kc tells me that I want to know the value of Kc. So, how do I write out my Kc expression? That's that products over reactants thing. Kc will be equal to the concentration of SO2 at equilibrium times the concentration of Cl2 at equilibrium divided by the concentration of SO2Cl2 at equilibrium. We don't have anything raised to any powers because we don't have any coefficients in the reaction itself. So plug in our values. 0.0239 times 0.0239 divided by 0.476. Now technically we do have molar in here because these are concentrations, but the Kc expressions are unitless. They're a ratio and we're not worried about units in them because they're telling us about the extent of a reaction. So you do ignore the units on a Kc expression. There isn't units on a Kc expression. And calculate this out and you'll find your Kc value to be equal to 1.20 times 10 to the minus third at 30 degrees C. So we've got 1.20 times 10 to the minus 3 at 30 degrees C. Now, what fraction of SO2Cl2 actually dissociated? How do we figure that out? Well, let's see. We know that we started with an SO2Cl2 concentration initial. Of 0.500 molar. We know at equilibrium we had a concentration of 0.476 molar. What this means is 0.0239 molar dissociated. That was the amount of the SO2Cl2 that actually decomposed to form SO2 and Cl2. This is the value that dissociated. I want to know this fraction compared to the whole. So the fraction dissociated divided by the total amount originally, 0.0239 divided by 0.500. These are both molar, so they do cancel out if you really want to worry about your units. And the fraction dissociated is 0.0478, or about 4.8%, just under 5%. Of the molecules dissociated. So on this example, let's focus on QC. Initially, what is QC? QC is our reaction quotient. So initially, SO2 initial, Cl2 initial, SO2 Cl2 initial. Initially, I didn't have any SO2 to start, I didn't have any Cl2 to start, and I had 0.5 molar SO2 Cl2 to start. So my value of QC initially was 0. QC was equal to 0. My Kc for this expression, or for this reaction, is 1.20 times 10 to the minus third. It's small, but it's bigger than 0. QC was less than Kc. So it tells me, yes, the reaction will proceed in the forward reaction. Now, some people may say, well, of course it's going to proceed in forward direction. We didn't have any of the products formed, so of course we expect it to form. That is correct, yes. However, sometimes you're going to be given initial concentrations for products as well, and you're going to have to calculate which direction is this reaction going to go, because you won't know without comparing that reaction coefficient to the K expression. Let's work another example. At 275 degrees C, the reaction below has an equilibrium constant Kc equal to 2.00. Suppose that 0.300 moles of PCl5 is placed in a 5-liter container at 273 degrees C. Gives me the reaction here. What is the direction of the reaction, and what will the concentration of each gas be once the system reaches equilibrium? First thing I need to do is figure out what is the concentration of PCl5 I have. I know that I have 0.3 moles, and I have a 5-liter container. So the concentration here, 0.600 molar PCl5. So first, what's the direction of the reaction? Well, we need to look at QC for that. My reaction coefficient, PCl3 concentration times Cl2 concentration divided by PCl5, 0 times 0 divided by 0.0600 gives me 0. So my QC is equal to 0, which is less than my KC, which is equal to 2. So which is the direction of the reaction? The forward direction. Reaction proceeds in a forward direction. Forming product. What about the second part of the question? What will the concentration of each gas be once the system reaches equilibrium? In order to do that, you need to set up an ice table. I'm going to erase the Q stuff down here for some space. Rewrite our equation, PCl5 in equilibrium with PCl3 plus Cl2. Initially, I have 0.0600 molar PCl5 and no PCl3 or Cl2 present. Change minus X for the reactant plus X for product. Because there's only 1 mole of each, it's just X and not a multiplet of X. In equilibrium, I have 0.0600 minus X, X, and X. Now I'm going to write out my Kc expression. I know that's my products over my reactants, so this will be equal to PCl3 at equilibrium times the concentration of Cl2 at equilibrium divided by the concentration of PCl5 at equilibrium. I'm going to plug in what the table tells me. I know I have X for PCl3, so I'm looking at these values here now, times X for Cl2, divided by 0.0600 minus X, which we can also write as X squared, divided by 0.0600 minus X. How is that helpful? Because I know what my Kc equals. I'm told in the original question that Kc equals 2. So this equals 2.00. Now we can do some algebra. So let's go ahead and simplify this. I'm going to multiply this to both sides. This gives me X squared equal to 2 times 0.0600 minus X. I'm going to distribute that through and get all the variables back on one side. And I have X squared plus 2X minus 0.12 equals 0. And I'm going to use the quadratic formula. To solve for the value of X. Remember, X equals opposite of B plus or minus the square root of B squared minus 4AC all over 2A. Plug all that in. You're going to get two values for X. X will either be equal to 0.0583 or X will be equal to negative 2.058. Now, here's the thing. The quadratic formula does not discriminate. It does not care. It's not real world. It's going to give you two values, a positive value and a negative value. You now are in the world of chemistry where we do care. So the positive value is correct. The negative value is just the way the math washes out, and it is not valid. So your answer here for the X value is the positive value. So therefore, now we can figure out the concentrations of the species at equilibrium. This means that the concentration, PCl3, at equilibrium is equal to 0.0583 molar. Concentration of Cl2 at equilibrium is also equal to 0.0583 molar. And the concentration of PCl5 at equilibrium is equal to 0.0600 minus 0.0583, which ends up giving me an answer of 0.0017 molar. You can always check your answer here as well. Go ahead and pause if you need to write this down. I want to write this stuff up here. So we know that the concentration of PCl5 at equilibrium is equal to 0.0017 molar. Concentration of PCl3 at equilibrium is equal to 0.0583 molar. And the concentration of Cl2 at equilibrium also equal to 0.0583 molar. And again, I did say that you can double check your work here, and you can. And if you have time, it's always a good idea to do. Rewrite out your Kc expression, or just don't erase it in the first place. And plug in the values you just found. Both of these are equal to 0.0583, so that's the same as 0.0583 squared, divided by 0.0017, and this gives me a value of 2, which matches to the overall system originally. So, when you're doing calculations involving equilibria, if all else fails, do these two things. Set up your ICE table. Your ICE table will hopefully get you back on track so that you can find the right answer. The biggest mistake students are going to make is they're going to forget to do their ICE table or their ICE chart, or they're going to forget that if there's a coefficient out front, it changes that value of X by that coefficient, and I will do an example like that next. But set up your ICE table, initial change equilibrium. You can also call this your RICE table for reaction initial change equilibrium. Anytime you write an ICE table out, you should always write the reaction out first. If it helps you remember to write the reaction by saying RICE instead of ICE, please do so, but remember the reaction must be written. And then plug your equilibrium values from that table into your Kc expression and solve as needed. So consider the following equilibrium. If I have 6 moles of NaCl and I place this in a 2-liter flask and allow this to react until there's no detectable change in the concentrations of reactants and products. At equilibrium, we found that the flask contains 1 mole of NO. How much chlorine gas is present at equilibrium, and what is the value of Kc for this reaction? Well, first, it's telling me that I have 6 moles of NaCl placed in a 2-liter flask. So that means I can figure out the concentration of NaCl. That tells me I have 3 molar NaCl to start. Let's go ahead and set up my rice chart. 2 moles of NaCl react to produce 2 moles of NO and 1 mole of Cl2. And I'm not specifying, but these are all in gas phase, and that does matter. We will see why when we talk about heterogeneous equilibria soon, but it absolutely does matter. Initial change in equilibrium. Initially, I have 3 molar NaCl. I don't have any NO present, and I don't have any Cl2 present. Now change, I'm going to say minus 2x. The coefficient out front becomes the coefficient on what's changing, since it's the number of moles that are changing. I have X number of moles reacting, but 2 of that for this reaction specifically. So I have to say 2 times that number of moles. this produces 2x moles of NO and 1x mole of Cl2. At equilibrium, I have 3.00 minus 2x moles of NaCl left, 2x for NO, and x for Cl, or Cl2. And again, I keep saying mole, this is molar. Ice tables are in molarity. Because it's all in the same system, it's all in the same container, it's all in 2-liter flasks, the reactions occurring, the number of moles are correlated back to the molarity. Now what do I do? Well, I don't have... How am I going to figure this out, right? Well, I am told that at equilibrium, my NO concentration is equal to, or I have 1 mole of NO at equilibrium. And I know it's in a 2-liter flask. So that's helping me. That tells me that NO at equilibrium (1 divided by 0.2) is giving me 0.5. So I have 0.5 molar NO at equilibrium. But I also know from my ice table that at equilibrium, NO concentration equals 2x. So that means that 2x is equal to 0.5 molar. I'm told I have 1 mole, and it's a 2-liter flask, which means it's 0.5 molar. I also know, based on my Rice chart, that at equilibrium, I have 2x molar of NO present. Therefore, 2x has to equal 0.5. What am I trying to solve? How much equal, sorry, I forgot what I'm trying to solve here. How much x is present? X, 0.5 molar, divided by 2, gives me 0.25. And this should have more sig figs on it. I'm dropping sig figs. Let's see, this should have 3 sig figs. This should have 3 sig figs, which means this has 3 sig figs. This value here is the concentration of Cl2 gas at equilibrium. So the chlorine gas, Cl2 gas, is 0.250 molar at equilibrium because chlorine gas is equal to x at equilibrium, whereas NO was equal to 2x. So now I know the value, how much chlorine gas I have present at equilibrium, 0.250 molar. What's the value of Kc for this reaction? It's the last piece of information I need. Well, now I know that this is 0.250 molar. I know that this is 0.500 molar. And I know this is 3.00 minus 0.500 molar, or the same as 2.50 molar. I can go ahead and set up my Kc expression. This equals NO concentration squared. Remember that these coefficients out front become the exponents in your Kc expression, times concentration of Cl2 divided by the concentration of NOCl, and that quantity is also squared because of the 2 out front. Plug in our values. These are all at equilibrium. Sometimes I write EQ, sometimes I don't, but these are all at equilibrium. Plug in our values, and we have for NO concentration at equilibrium, we have 0.500, that quantity is squared. For Cl2, we have 0.250, and for NOCl, we have 2.50. That quantity is also squared. And when you calculate this out, you should get a Kc value 0.0100. And remember, there are not units on this. So the Kc expression here, Kc equal to 0.0100. So a lot of work, but you guys have now figured out the concentration of Cl2 at equilibrium and the Kc value, or Kc expression at equilibrium. Let's work one more example. The equilibrium constant at a certain temperature for the below reaction is 100. So that's telling me Kc equals 100 at whatever temperature I'm working at. If I have 1 mole each of H2 and I2, and I place these in a 1 liter flask, what will be the concentration of each gas when the reaction is allowed to reach equilibrium at the given temperature? Set up your ice table. I'm told I have 1 mole of H2 in a 1 liter flask, which means I have 1 molar. I'm told I also have 1 mole of I2 in a 1 liter flask, which means I also have 1 molar I2. And I don't have any HI to start. H2 is the reactant, I2 is the reactant, so it's minus X minus X. HI is a product, so it's going to form it. And there's a 2 coefficient out here, so we're going to say plus 2X. At equilibrium, 1.00 minus X, 1.00 minus X, and 2X. Go ahead and set up your Kc expression. HI concentration squared divided by my H2 concentration times my I2 concentration. Go ahead and then we know, it tells me in the question, this equals 100. Plug in my values from my ice table. Kc equals 2x quantity squared divided by 1.00 times 1.00 minus x. I think I forgot to say minus x a second ago, but it should be minus x. I'm going to simplify the way this is written slightly. And hopefully you recognize at the point that this is a perfect square, which makes my life easier because now I don't have to remember the quadratic equation. Like, I know it, but I don't prefer to use it if I don't have to. I'm going to take the square root, both sides. When I do that, I'm left with 2x divided by 1.00 minus x equals 10.0. So square root of 2x squared, but that 2x is in parentheses, becomes 2x. The square root of 1 minus x in parentheses squared becomes 1 minus x, and square root of 100 is 10. I'll go ahead and do the algebra manipulation here to solve for x. 2x equals 10.0 times 1.00 minus x. You can simplify that. 2x equals 10.0 minus 10.0x. Get your x's to the same side. 12x equals 10.0. Continue up here because I'm going to run out of space. Solve for x. X equals 10.0 divided by 12. This gives me 0.833. That is a molar value. And I want to know the equilibrium concentrations of each species. So at equilibrium, H2 is equal to 1.00 minus 0.833 molar, 0.17 molar. At equilibrium, I2, 1.00 minus 0.833, also 0.17 molar, and HI is equal to 2x. So 2 times 0.833 equals 1.67 molar. So H2, 0.17, I2 also 0.17, HI 1.67. 1.67. So the important part for this question specifically is to realize that sometimes you don't have to use the quadratic. Could I have solved it with quadratic? Yeah, and I'll get to the same point, but I don't like using it if I don't have to. So when you have a perfect square, it just makes the math a little bit easier to deal with. But you do need to be strong in your algebra to be able to do these calculations correctly.